Hello. Let's see. So here's our next our next element of this unit. Um, so block 4, you saw this to start or to end the unit. Sorry, to end the lesson yesterday. Oy, my first video in a while. Block 1, you did not see this. Now this looks block 1 like one of those that I said I wouldn't ask you about, but here's why. Here's why I am asking you about it. This question asks you to find the potential difference between 2 points, between point A and point B in this here circuit. All right. Now, this looks like a combination circuit and also a complex circuit. Combination meaning there are both series connections and parallel connections. Complex meaning there are multiple batteries in multiple locations. Well, the deal is this. As a first step, what you want to do is find I total. All right. If you notice, there is not a connection here. So that means that in this whole section, there's no current. And so the only path of current is this one. All right. So in terms of finding current and finding equivalent resistance and stuff, the only batteries / resistors you need to worry about, and currents you need to worry about, are in that outside loop. So that makes this not really a combination circuit. All right, that's one big deal. All right, so for everybody, we want to find the potential difference between point A and point B. Okay, remember, no current in this middle branch. And what I'll say is, use this as a reference. Even though we're not talking about relative to ground like we did here, we're talking about the difference between the potential in 2 points. So you're either going to start at point A and, yeah, I would start at point A and either go this way around to point B or go this way around to point B. You figure out, looks like a butt, you figure out which way you should go, okay, based on which way current actually flows. Now, the other thing is this. This also, I realized, leads us into our new little element because of this, and this, and this. All right? That gets at the idea of what we call internal resistance. All right? So let me just back up and say that this is your homework. All right, this is part of your homework. The rest of it is to take these notes. It won't take too long. All right, but in order to do this right, this is more for block 1. Block 4, you sort of got a little heads up on this. But for block 1, folks, what we're saying here is that even power supplies can have, this is, for all intents and purposes, a battery. All right, a battery has, or all power supplies have what we call internal resistance. Okay, and it gets at this idea. I take a little cell out of my desk drawer, and I hook it up to a voltmeter, and it's going to read 1.5 volts. That's the potential difference of a brand new AA or AAA or C, or there's no single A, but yeah, any of those, even a D, I think. Yeah, they're all 1.5 volt cells. Okay. However, the brand new one or the one that I drag out of my drawer, that battery or cell, if you put it what we call under load, I make it actually try to light a lamp, and we're going to end up, with varying degrees of success. All right, the actual output of that cell can be different than what it says it's capable of. All right, the voltmeter by itself across the terminals of a battery might read 1.5 volts. But if I hook it up in a circuit, it might read something different. All right, and that's because everything has what's called an internal resistance. So a dead battery, here's the deal. If we imagine, we'll end up, let me put all this up here. Yeah. So to see what kind of room I have. You know what? Forget that this says energy and power. Just assume this is a blank page and I'm taking some extra notes on. So what we have, when we draw a battery, is we just do that, or a cell, right? And we have a real, like, load resistor here. This might be, forget about a load resistor, let's just call it, let's say this is a lamp, right? This is a flashlight, a simple flashlight circuit, right? Well, if we say that this has potential difference equal to 1.5 volts and some little internal resistance, say, equal to half an ohm, and this has some actual resistance of, say, I don't know, 25 ohms. Well, this is just like saying, you'll see these sometimes like this. You'll either see it like this, with the potential difference and a little r, or sometimes you'll see it like this. You'll see that and a little resistor. But typically what they'll do is they'll draw this box around it. So they're referring to this as the internal resistance. Now, I am not saying that if you crack open a battery, you'll find a little resistor in there, right? That is not the case, all right? But it's some function of the, how much electrolyte is in there, or how much acid is in there, or the condition of the salt bridge, or something like that. It ends up acting like a resistor, all right? But there's not real resistors inside batteries. But properties of the batteries make it behave like there are. All right, but the nice thing about it is when we see a case like this, and it tells us that there are some internal resistors in there, what we can do is redraw and just say, okay, fine. There's an 18-volt battery and a little 2-ohm resistor and a little 8-ohm resistor and a 3-ohm resistor, and here's B, and here's the 6-ohm and the 12-volt and the 5-ohm. So you can just draw them right in there, right? It's just like the resistors are actually there. Fair enough? All right. So the deal is this. We have these couple of quantities. There's the actual potential difference, what we call the loaded terminal voltage. You'll really more often see it just as terminal voltage, not loaded terminal voltage. All right? But the terminal, sometimes you'll even see it, sometimes we write it as this, the terminal potential difference. VPD, okay? Well, what you're actually going to get out of the battery depends on the EMF of the battery, what the battery is actually capable of, and how much current actually flows, and how much internal resistance the battery has. Okay? So, if we have a circuit like this, and we say that across here, there's some EMF. Across here, there's some terminal potential difference. All right? The EMF involves only the battery. Only what the battery is actually, sort of nominally capable of. All right? The terminal potential difference involves what the battery is nominally capable of, plus what its internal resistance sort of limits it to be able to do. Okay? And what we say is that, get rid of this stuff. This might be the 1.5 volts on the side of the battery. Hey, this battery is a 1.5 volt battery. Sure it is, except, if we actually make it run some current, based on how much resistance has built up in it, well, sometimes, when this IR gets to 1.5 volts, well, then that means delta V, or V potential, or the terminal potential difference, then that's going to be 0. And that's what we call a dead battery. All right, you yank a battery out of a dead flashlight, hook it up to a voltmeter, it'll probably still read 1.5 volts. And you say, well, heck, why doesn't it work? Well, it's because the condition of the battery is such that its internal resistance has built up enough that you lose all that potential in the battery itself instead of losing it across the bulb. What do you think? I get a feeling I didn't do a great job at that. All right, but here's a sample question. The question says there's this generator that has a terminal voltage, or a terminal potential difference, of 110 volts when it's delivering 10 amps. But notice, when it delivers 30 amps, the terminal potential difference drops down to 106, right? So based on how much current flows, this number, the terminal potential difference, can change. Now, what doesn't change is the EMF, right? Just like we said, our battery, no matter what, it says on the side 1.5 volts. Well, that's its EMF. That's what it's nominally capable of doing. All right? So we can say that in each case, E is constant. VPD depends on I and R. Well, and E. So I'm going to say that E1 is equal to E2. Right? E is the same no matter what. So there's two different EMFs. I can say that delta V plus IR, 1, 1, and 1, is delta V2 plus I2R2. Right? I'm just rearranging this. If delta V is E minus IR, then E is delta V plus IR. Okay? Now, what we're looking for the EMF and the internal resistance. Well, notice here, R is constant. Well, E is constant, and in a certain state, this generator has a certain internal resistance. Okay, that doesn't depend on current. It doesn't depend on EMF. So we can really say that R1 is R2. So we'll just solve this for R. Okay, we're going to get delta V1 minus delta V2 equals I2R2 minus I1R1. Well, sorry, let me rewrite this. Since the R's are all the same, I2R minus I1R. Okay, or delta V1 minus delta V2 equals R times I2 minus I1. Or delta V1, 110 volts. Delta V2, 106 volts. So that's 4 volts. I2, 30 amps. I1, 10 amps. 20 amps. So that means that R is 0.2 ohms. Right? It's got this little, relatively small internal resistance. Okay? Well, we can take this and plug it into either of these expressions to find E. So we can do 110 plus 10 times, 0.2, no, sorry, 110 plus 10 times 0.2. That's 110 plus 2, or 112. That gives me an EMF of 112 volts. Or we could do, right, 106 plus 30 times 0.2. 106 plus 6. Oh yeah, 112. Right? So there's our solution for this one. What do you think? Okay? So the idea again is that every power supply has some internal resistance. You're going to lose some potential right inside the power source itself. All right? Ideally, the power source's internal resistance is small enough so that you don't lose too much potential inside the source. You can use most of it, to, in this case, light the lamp. All right? Okay. So in this one, like I said, when it comes down to solving problems with these things in circuits, you just go from this to drawing it. Here's the 2 ohm resistor. Here's our 8 ohm resistor. Here's our 6 ohm, and here's our 5 ohm. Here's the 3 ohm. Here's the 1 ohm, and here's the 4 ohm. All right, you treat them just like a regular old resistor. All right, and there's potential differences across them, I times R. Okay? All right, folks. I will see you tomorrow with a bunch of what do you call them? Internal resistance problems to work on. Okay, folks. Adios.